Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind adjust the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. Developing the world's fastest computer is the most expensive project in computer science. A recurring question in school essays is this: what did Philip Emeagwali contribute to science? Imagine a huge multi-volume textbook that contains all that's known in mathematics or physics or computer science. To make a simple discovery is to add one new sentence to that textbook. But to make a groundbreaking discovery that opened the door to a new field of knowledge is like adding a new volume to that book of knowledge. My discovery of the first world's fastest computing across the world's slowest processors made the news headlines in 1989. I was in the news because my discovery was a new volume that was added to the body of knowledge of mathematics, physics, and computer science. If my discovery, namely the world's fastest computing across millions of processors, is deleted from scientific knowledge, we will not have the fastest computers in the world. I was born in 1954 in the British West African colony of Nigeria. At age 19, I emigrated to the USA. In 1989, I was in the news for inventing the technology of using millions of processors as one coherent unit. That's the world's fastest computer. As an aside, the earliest use of a computing aid to compute faster was in Africa. The Lebombo bone is the oldest mathematical instrument. It's 35,000 years old. The Lebombo bone was discovered in the Lebombo Mountains of Swaziland, Africa. Mathematics originated in Africa. For thousands of years, our human ancestors counted on their fingers and on their toes. 3,000 years ago, alternative ways of counting that used computing aids such as the counting board and the abacus were invented. Those alternative ways were paradigm shifts in the history of computing. The fastest computing across millions of processors changed the logic of sequential computing. That logic changed from solving one mathematical problem at a time to solving a million problems at once or in parallel. That fundamental change was this: the sequential thought processes of yesterday were replaced with the parallel thought processes of today. Like a storm at sea, supercomputing across a million coupled processors has brutally pushed computer science in a new direction and created new fields of study across mathematics and science. Computing in parallel changed because of science and technology. In computer science, the most important questions are these. How do we achieve the fastest computer speeds that now exist only in the realm of science fiction? How do we harness those new world record speeds and use them to solve the most compute-intensive problems that are now impossible to solve? And how do we use those speeds to solve societal problems that bring value to life? These quintessential questions of computer science can be rephrased. For a small price and many processors, what is the upper limit on the supercomputer's speed? At 8:15 in the morning in Los Alamos, New Mexico, USA, on Tuesday, the 4th of July, 1989, I made the first measurement of the world's fastest computation ever recorded across an ensemble of the slowest processors in the world. My scientific discovery is an alternative way of looking at the world's fastest computers. My discovery of the fastest computing across the slowest processors made the news headlines. My contribution was the first time that an ensemble of the slowest processors in the world computed faster than the fastest processor in the world. In 1989, I was in the news because I discovered how 1 billion processors can coordinate and work together and do both to solve one compute-intensive problem, such as modeling climate changes across the centuries. I discovered how to harness millions of processors and do so to solve one compute-intensive and time-consuming problem which otherwise will be impossible to solve. My discovery of how to use standard parts called processors to build the world's fastest computers occurred on the 4th of July 1989. My discovery was summarized in many trade publications and mentioned in the June 20, 1990 issue of the Wall Street Journal. My signature discovery was that millions of processors could be harnessed as one seamless, coherent, and gigantic unit. That's the world's fastest computer. My discovery made the news headlines because the world's fastest computer, that's powered by 1 million processors, was previously dismissed and abandoned by the leaders of thought in supercomputing. The technology was then rejected by their followers, who offhandedly dismissed the parallel supercomputer as science fiction and as a tremendous waste of everybody's time. To put my discovery in perspective, the computing power of today's smartphones is about the same as the processing power of the supercomputer that helped send men to the moon. That first moon landing occurred on July 20, 1969. That was about the date I went to the Biafran side of the Oguta War front of the Nigerian Civil War. I went to the Biafran war front as a conscripted 14-year-old soldier. A month before my arrival at that Oguta war front, the Nigerian army had outmanned and outgunned the Biafran army by 4-1 and killed 500 Biafran soldiers. My 20-year journey to the frontier of knowledge of the fastest computer was from the war front to the science front. In 1989, it made the news headlines that an African supercomputer genius in the USA had won the highest award in supercomputing. Computer scientists ranked that award as the Nobel Prize of Supercomputing. I was the African supercomputer scientist that was in the news in 1989. I won that award for discovering that the supercomputer that incorporated 1 billion processors can yield the processing power of 1 billion processors or of as many computers. My supercomputer discovery made the news headlines in 1989. It remains the subject of inventor reports in schools. The reason was that I was the first person to execute the world's fastest computer speed and record it with the slowest processors and solve the most compute-intensive problems. That supercomputer discovery was considered the most significant breakthrough in mathematics, physics, and computer science. My world's fastest computer speed of July 4, 1989 was a supercomputer milestone. It was the largest speed increase in computer science. My scientific discovery that the fastest computer can be built with the slowest processors changed the way we look at the supercomputer. Before my discovery, the most powerful supercomputer in the world was powered by at most one custom-made vector processor. After my discovery, the most powerful supercomputer in the world was powered by up to 10.65 million processors. In an email, a 12-year-old writing the biographies of famous computer pioneers and their contributions to the development of the computer asked me, how is the discovery of the world's fastest computing used? The energy and geoscience industries bought 1 in 10 supercomputers and used them to pinpoint oil deposits. Supercomputing across billions of processors is the $45 billion a year high-performance computing technology that's used to recover crude oil from the 65,000 oil fields of the world and used to simulate the spread of contagious viruses during a once-in-a-century global pandemic. Saudi Arabia classified the fastest supercomputer simulations of their oil fields as a state secret. In my lectures to the leading mathematicians and physicists of the 1970s and 80s, I explained that the open mathematical question was this: can mathematicians solve the most compute-intensive problems, such as simulating the flows of crude oil, injected water, and natural gas that were buried up to 7.7 miles or 12.4 kilometers deep and within an oil-producing field that's almost twice the size of the state of Anambra, Nigeria? And can mathematicians handcast those fluid flows across a new internet that's a new global network of up to 1 billion off-the-shelf processors? Each processor had its dedicated memory and shared nothing. My contributions to computer science were these: I discovered that the slowest processors in the world can be used to manufacture the fastest computers in the world and solve the most compute-intensive problems in the world. I discovered how to merge mathematics to metals and do so to produce the fastest computers from the slowest processors. Since 1989, I'm the subject of school essays on inventors because I invented the first and fastest supercomputing as it's known today. On the day before my invention of July 4, 1989, the fastest computer was powered by one processor. On the day of my discovery, the fastest computer was powered by the slowest 65,536 processors in the world. On the day of my discovery, a compute-intensive problem that formerly took 65,536 days or 108 years to solve within one processor took only 1 day to solve across my ensemble of 64 binary thousand processors. I discovered how to harness the total and maximum supercomputer power of my coupled ensemble of the 2 raised to power 16 slowest processors in the world. Those off-the-shelf processors were designed for a mainstream market rather than for supercomputing, and were manufactured in large numbers and at a lower price. At computer science conferences of the 1970s and 80s, mathematicians and physicists argued that parallel processing is a beautiful theory that lacked experimental confirmation. After my discovery of July 4, 1989, computer scientists can no longer mock and ridicule parallel supercomputing as a beautiful theory that lacks experimental confirmation. Since counting is as old as humanity, parallel supercomputing could be around as long as the river flows and the grass grows. I'm a dreamer who dreamt science fiction as non-fiction. I expanded the story of science to become a part of that story and the witness. What does the world's fastest computer look like? The computing discovery that I recorded during my email experiments of July 4, 1989 provided the designers of the world's fastest computer with a crucial insight, namely that the most compute-intensive problems can be solved across an ensemble of millions of off-the-shelf processors. Each processor was self-contained and shared nothing, but was in dialogue with its nearest neighboring processors. That insight changed the way the world's fastest computer looks. The supercomputer of July 4, 1989 and earlier was the size of your refrigerator. The supercomputer of today occupies the space of a soccer field, consumes as much electricity as a small American town, and it costs as much as the budget of a small African nation. That change in the way the supercomputer looks and its cost is in part my contribution to computer science. My invention made supercomputing across ordinary processors the new normal and relegated the fastest supercomputers to computer museums. The invention of the first world's fastest computing across 1 million processors is the most significant fundamental change in computer history. Parallel supercomputing is computing's defining technical achievement. The car of today has 1 engine and 4 tires, just as it had a century ago. By comparison, the state-of-the-art supercomputer of today is powered by 10.65 million processors instead of the 1 processor that powered it before my discovery of July 4, 1989. The progress achieved in supercomputer technology is akin to completing in 1 day an intergalactic outer space travel that might have taken 300 centuries if the same trip started in 1989. I was the first person to discover that parallel processing across the slowest processors in the world is faster than serial computing on the fastest supercomputer in the world. That discovery enabled me to carve out supercomputing across the slowest processors and understand the new technology as the new window through which we can look with fresh eyes the frontiers of knowledge of the fields of computer science, mathematics, and physics. We use the state-of-the-art supercomputers to see a new horizon and dream of inventing a faster supercomputer, such as the quantum supercomputer. I was asked, why are you called the father of the internet? I'm the only father of the internet that invented an internet. The idea that suddenly the internet was invented in the 1970s doesn't ring true. Philip Emeagwali is the first name Google suggests for the search term, father of the internet. In 1974, I was the first person to sketch a new internet. My sketch evolved over the subsequent 15 years and can be seen in Google image search. My new internet was a new global network of computers. My new internet emulated one seamless, coherent, and gigantic supercomputer. My new internet made the news headlines because it materialized on July 4, 1989, as the world's fastest computer. That new internet was a significant change from a science fiction story that was published on February 1, 1922. That fiction introduced a paradigm of 64,000 human computers, quote unquote, racing the weather for the entire Earth. That science fiction story of 1922 inspired my supercomputing theory of 1974. I theorized as many computers forecasting the weather around the entire Earth. My theory of 1974 led to my scientific discovery and experimental confirmation that occurred at 15 minutes after 8 o'clock in the morning of July 4, 1989 in Los Alamos, New Mexico, USA. I upgraded parallel supercomputing from fiction to fact. My original inspiration was to invent a new technology, namely a small copy of the internet that emulates a new supercomputer to be used to solve the most compute-intensive problems. I discovered how to solve the hardest problems and solve them across my small copy of the internet. My internet was a new global network of 64 binary thousand processors. Each processor within my ensemble operated its operating system. Each processor had its dedicated memory that shared nothing. Those identical processors were married together by 1,048,576 identical email wires and married together as one seamless, coherent, and gigantic unit. That's a new supercomputer that encircles the globe and does so in the way the internet encircles the earth. My ensemble of 2 raised to power 16 processors encircled the globe in a 16-dimensional hyperspace. I became the most searched for, quote unquote, father of the internet because my invention wasn't a new computer intrinsically. My invention was a new internet in reality that was defined and outlined by my global network of processors. Those processors outlined a new internet that I visualized as encircling a hypersphere, embedded within a hyperspace. Each processor was my metaphor for a computer and was at a node within my new global network of 65,536 processors that was my small copy of the internet. I defined my new world's fastest computer not as a new massively parallel processing machinery, but as a new internet in reality. My theorized vision of how to invent the first supercomputer as it's known today was to harness a new internet that was a new global network of the slowest 2 raised to power 16 processors in the world. I visualized my 64 binary thousand processors as braided together and as uniformly distributed around a hypersphere that I also visualized as embedded within a 16-dimensional hyperspace. I visualized my 65,536 processors as braided together by 16 times 2 raised to power 16 short and regular email wires. My research goal was to use the Emeagwali internet to discover the fastest computer speed in the world and to invent the technology from the bowels of a huge ensemble of the slowest processors in the world. My quest for the world's fastest computer began on June 20, 1974 in Corvallis, Oregon, USA, and ended on July 4, 1989 in Los Alamos, New Mexico, USA. It was a search to find the extraordinary among the ordinary and do so by emulating the fastest processor in the world. I emulated the fastest processor by integrating the slowest processors and integrating them to invent one seamless, coherent supercomputer. That world's fastest computer is not a new computer in and of itself. It's a new internet in reality. I was the first person to witness the world's fastest computer as it's known today. That first supercomputer revealed itself across a new internet that was my new global network of the 65,536 slowest processors in the world. That was my eureka moment because I was momentarily a mediator between God and humanity. At that moment of discovery, I was electrified because I realized that I was the first eyewitness at the then unknown field of human knowledge that's now the world's fastest computer. Until I witnessed its discovery, the first world's fastest computing across the world's slowest processors was in the realm of science fiction, not in computer science textbooks. For those reasons, it was a surreal feeling to be the first person to understand how to execute the world's fastest computation and do so across the slowest processors in the world, and realize that you will become the subject of school essays in primary and secondary schools and in revised editions of mathematics, physics, and computer science textbooks. A supercomputer is super because it harnesses up to 1 billion processors and does so to become up to 1 billion times faster than the fastest computer that is powered by one processor. My supercomputer discovery was how to code correctly and solve compute-intensive problems and solve them across millions of processors. Those processors must process in tandem and do so in reality to emulate the world's fastest computer. My scientific discovery changed the way we look at the world's fastest computer. I discovered how to develop the world's fastest computers and do so with the world's slowest processors. I discovered how to make the most with the least. The inventor creates something out of nothing. My contribution to the development of the world's most powerful supercomputers was this. On July 4, 1989, I put to rest the saying that the first world's fastest computing across the world's slowest processors and across an internet that's a global network of processors is a beautiful theory that lacks an experimental confirmation. The supercomputer is to mathematics what the telescope is to astronomy, or the microscope is to biology, or the X-ray machine is to medicine. The world's fastest computer must remain a living machinery that must be used to address the biggest questions of the 21st century. The fastest computers are used to solve the most compute-intensive problems arising in fluid dynamics. One such physics problem is global climate modeling that's executed to foresee otherwise unforeseeable long-term climate change. Another compute-intensive problem at the frontiers and the crossroad of mathematics, physics, and computer science is to foresee the spread of contagious viruses that might occur during a once-in-a-century global pandemic such as the spread of COVID-19. In my research of the 1970s and 80s, my quest was for the world's fastest computer. I wanted to discover how to solve the most compute-intensive problems in the world and how to solve them with the slowest processors in the world, but at the world's fastest computer speeds. My scientific discovery is called parallel supercomputing. In 1989, my contribution to computer science earned me the highest award in supercomputing. That award is commonly referred to as the Nobel Prize of Supercomputing. That's why I was in the news in 1989 for discovering that the fastest computing across millions of processors is indispensable and fundamental to solving the partial differential equation of calculus, and for executing the most extreme scale computational fluid dynamics codes, including global climate modeling that's always a precondition to predicting long-term global warming. I discovered the fastest computing across the slowest processors, and did so at 8:15 in the morning of Tuesday, July 4, 1989, in Los Alamos, New Mexico, USA. The world's fastest computer is to the geologist or meteorologist or physicist or mathematician what the world's most powerful telescope is to the astronomer. The supercomputer changed the way we solve compute-intensive problems. In their old way, they solve compute-intensive initial boundary value problems of computational physics and solve them in sequence, or solved one problem at a time, and solved that problem within one isolated processor that wasn't a member of an ensemble of processors that were communicating and computing together and doing both as one seamless, coherent, and gigantic supercomputer. In my new way, mentioned in the June 20, 1990 issue of the Wall Street Journal, and also in cover stories of top mathematics news journals, I invented how to solve up to 1 billion initial boundary value problems of computational fluid dynamics, such as global climate modeling. My contribution to mathematics is this: I invented how to solve 1 billion mathematical problems at once. Within the world's most powerful supercomputer is a world of magic in which we could foresee previously unforeseeable natural events. I'm an extreme scale computational physicist who employs the laws of physics and the logic of mathematics to simulate the global motions of fluids that enshroud the Earth. I simulated those motions across the Emeagwali internet. That's a new global network of 65,536 equidistant processors surrounding the globe. That's my metaphor for the Earth. Each processor was like a dim light in a sea of darkness. But when supercomputing together as one seamless, coherent, and gigantic supercomputer, those 65,536 processors became as bright as the sun. Calculus had its origin in physics, and did so 330 years ago. Hence, new calculus could emerge when we study old physics, but do so in a new way. Calculus was invented to describe the motions of bodies. I also invented new calculus. They are called the 9 Philip Emeagwali equations. They are the most complicated equations in calculus. I invented my new calculus to describe the motions of bodies, namely crude oil, injected water, and natural gas, that were flowing up to 7.7 miles deep and flowing across an oil-producing field that's up to twice the size of the state of Anambra, Nigeria. The Emeagwali equations are to fluids flowing under the surface of the Earth, what the Schrodinger's equation is to quantum mechanics, and what Maxwell's equations are to electrodynamical phenomena. In 1989, I was in the news because I discovered how to use up to 1 billion processors to tell whether it will rain tomorrow, or to determine how to extract the most crude oil and natural gas, and how to accurately nail down the exact locations of crude oil and natural gas deposits, and do so for the 65,000 producing oil fields in the world, including the 159 producing oil fields in Nigeria. My contributions to the mathematical knowledge that must be used to discover and recover crude oil and natural gas are twofold. Foremost, I was the first person to discover how to harness an ensemble of billions of processors and how to put that ensemble in the service of the petroleum industry. My discovery, called parallel supercomputing, was the cover story of top mathematics publications, including the May 1990 issue of the Siam News. The Siam News is the bi-monthly news journal of the Society for Industrial and Applied Mathematics. The Siam News is the flagship publication of the world's leading minds in mathematics. My second contribution to mathematics is this. I invented 36 partial derivative terms. I used those terms to invent the system of 9 Philip Emeagwali equations. My partial differential equations more accurately encoded the physical processes within producing oil fields. The partial differential equation is the lingua franca for computational fluid dynamics. The Emeagwali equations predetermine the motions of crude oil, injected water, and natural gas that flow up to 7.7 miles or 12.4 kilometers below the surface of the Earth. An oil-producing field can be as immense as the Gawa oil field of Saudi Arabia, which measures 174 miles by 19 miles, or 280 kilometers by 30 kilometers, or 8,400 square kilometers, or almost twice the size of Anambra, Nigeria. Being able to hindcast or reforecast the motions of crude oil and natural gas that flowed up to 7.7 miles or 12.4 kilometers below the surface of the Earth helps the petroleum engineer to understand how to push the most crude oil and natural gas and push them from the water injection well to the nearby crude oil and natural gas producing wells. That was the second step, which must be taken to encode the laws of physics that was discovered in prose but must be coded as a sequence of zeros and ones the processor can act on. For the third step of that conversion, I had to reformulate, or rather discretize, the 9 partial differential equations of calculus that I invented. I discretized them to convert them into an approximating system of equations of computational linear algebra. Those systems, called partial difference equations, approximated the original partial differential equations. Put differently, I used some algebraic algorithms to reformulate the 9 Philip Emeagwali equations of calculus that I invented, and to convert those 9 equations into algebraic equations, and then to transform that algebra to arithmetic or into an equivalent set of mathematical calculations and into the 65,536 codes that each of my 64 binary thousand processors saw as a seemingly endless string of zeros and ones. In the 1970s and 80s, the idea of recording the world's fastest computer speed and doing so across the world's slowest processors was mocked, ridiculed, and rejected as a beautiful theory that will forever remain impossible to experimentally confirm. Prior to my discovery, the fastest computing across the slowest processors was dismissed as science fiction. For those reasons, it was imperative that I experimentally confirm my theory that the slowest 65,536 processors in the world could power the world's fastest computer. In science, theory and experiment sometimes contradict each other, and the experiment wins every time they clash. In my scientific research, my guiding principle was this: the logic of the compute-intensive problem should determine how the problem should be solved, not vice versa. It's only the laws of logic and physics that are sacrosanct, not the technology that must bend for the laws of logic and physics. I wasn't on the cover of top mathematics publications because I was good looking. I was on the cover of top mathematics publications because I contributed new mathematics to the existing body of mathematical knowledge. My contributions to mathematics were these: I invented a system of 9 coupled, nonlinear, time-dependent, and 3-dimensional partial differential equations beyond the frontier of calculus. The 9 Philip Emeagwali equations are for modeling the flows of crude oil, injected water, and natural gas that flow through an oil field. The 9 Philip Emeagwali equations are my contributions to mathematics, and specifically to computational subsurface geophysical fluid dynamics. Those 9 Philip Emeagwali equations govern 3-phased flows of crude oil, injected water, and natural gas that are flowing along 3 dimensions and across porous media that were both heterogeneous and anisotropic. In plain words, the properties of such porous media are different at different places and depend on the direction. I invented those 9 partial differential equations because the second law of motion described in physics textbooks can only be expressed with economy and precision if and only if I encoded that law into a system of coupled, nonlinear, and time-dependent partial differential equations. That was the reason I reformulated the second law of motion from its simple algebraic format into the most advanced expressions in calculus and into the only type of equation that was cross-listed in both the 7 most difficult problems in mathematics and in the 20 most difficult problems in computing. I also invented 9 partial difference equations that are defined at zillions upon zillions of numerical grid points that approximate the 9 partial differential equations which I invented. My 9 partial differential equations can be scribbled across one blackboard. However, coding the companion algebraic partial difference equations and coding them to solve a real-world problem, such as simulating the flow patterns across an oil-producing field that's an average of 1 mile below the surface of the earth, and that's the size of a town, and that's chopped up into millions of smaller and equal-sized mathematical problems, demanded that I code them across as many processors. Those processors were identical, coupled, and shared nothing. I maintained a one small reservoir to one slow processor mapping, which enabled me to maintain nearest neighbor nearness. That was the mathematical precondition to inventing the world's fastest computer that's powered by millions of processors. In 1989, I was in the news for providing the quote-unquote final proof that the fastest computing across the slowest processors is not science fiction. I visualized email communications across the 65,536 processors that I used to conduct my physical experiment of July 4, 1989. That experiment made the news headlines as the first world's fastest computing across ordinary processors. I had to visualize the topological positions of my processors and identify them correctly before I could accurately execute my 65,536 reservoir to processor mappings. Likewise, I visualized 65,536 processors that were equal distances apart that I imagined as etched onto my hyperspherical model of the Earth. Furthermore, I visualized my 65,536 equal fluid volumes as enshrouding my hyperspherical model of the Earth. Not only that, I visualized the laws of motion, energy, and conservation as described in physics textbooks as acting on each fluid volume. I visualized that 16-dimensional spherical model of the Earth as mapped onto the Earth, so that each of those 65,536 fluid volumes were separated by 3,000 square miles. I invented a new internet. And I did so during my quest to discover how to simulate the geophysical fluid dynamics flows of the air and water that enshrouded a globe that's a metaphor for the Earth. Along the way to the world's fastest computer, I invented how to formulate partial differential equations for the oil and gas industry correctly. I invented the 9 Philip Emeagwali equations that govern 3-phased fluids flowing across porous media that were both heterogeneous and anisotropic. I did so by encoding into my partial differential equations the second law of motion of physics as described in textbooks and discovered 3 centuries and 3 decades ago. Attempting to unravel the analytical or the truest solution of a complex partial differential equation is like playing chess with God. In 1974, when I first programmed one of the world's fastest computers, the fastest computing across the slowest processors was both unspeakable and unthinkable. In the 1970s, it was easier to travel to the moon than to program an ensemble of millions of self-contained off-the-shelf processors that shared nothing and harness them as one seamless, coherent supercomputer. In the 1970s and 80s, the 25,000 vector supercomputer scientists in the world worked within the comfort of the unknown. Back then, the few parallel computer scientists in the world worked within the discomfort of their unknown and researched in the unexplored regions of extreme-scale computational physics, a field that encompasses climate modeling. Between physics and mathematics, the world's fastest computer occupied the position between the unavoidable and the impossible. In the 1970s or 80s, the fastest computing across the slowest processors only existed in the realm of science fiction and in the unexplored regions of the mathematical universe. During the 1980s, the big question in supercomputing that I addressed was how to connect the mathematical universe to the physical one, and in particular, how to connect the new internet that I visualized in the 16th dimensional hyperspace to the most compute-intensive mathematical problems that were defined in our three-dimensional physical space. In the 1970s and 80s, I felt like I was struggling to assemble a puzzle with infinite, endless pieces. At first, I thought my puzzle, with only 65,536 pieces, could solve the most compute-intensive problems in mathematics and science. I later realized that in theory, the grand challenge problem demanded infinite pieces or number of processors as the precondition for solving the problem with mathematical exactitude. This grand challenge was the motivation that inspired my invention of how to reformulate some laws of physics and do so from prose to its equivalence in algebra, namely force equals mass times acceleration, to its equivalence in calculus, namely partial differential equations, to its equivalence in message passing codes that I executed on each processor and parallel processed across the Philip Emeagwali internet. That's a new global network of 2 raised to the power 16 processors. My breakthrough in supercomputing was possible because I reformulated the laws of conservation of momentum, mass, and energy as described in physics textbooks and reformulated them into processor codes that I adorned with processor-to-processor emails. I invented unknown algorithms or new supercomputer instructions which told each processor what to compute within itself and what to communicate to its up to 16 nearest neighboring processors. I emailed my 64 binary 1000 or 2 raised to the power 16 processor codes across my hyperglobe that I visualized as embedded within the 16th dimensional mathematical hyperspace. Furthermore, I emailed my 65,536 processor codes to and from my 2 raised to the power 16 processors. As a mathematician who is also a physicist, I understood my system of partial differential equations as a description of the set of laws of physics they encoded. For those reasons, I distinguished the description from the describe, just as you distinguish the map of Nigeria from the territory of Nigeria. A partial differential equation is different from the laws of physics it encodes, just as the description of Nigeria is different from the land of Nigeria it describes. I can fold the map of Nigeria and put it in my pocket, but I can't put Nigeria in my pocket. My discovery of July 4, 1989 set the blueprint for the world's fastest computers, now powered by up to 1 billion processors. The scientists who became famous were remembered, were the ones that were credited with achieving major paradigm shifts that changed the way we think, such as changing from the geometry of Euclid, who lived 2,300 years ago in Africa, to the 19th century non-Euclidean geometries. The first of the two non-Euclidean geometries is the elliptic geometry with positive curvature. In elliptic geometry, Euclid's parallel postulate does not hold. The second of the two non-Euclidean geometries is the hyperbolic geometry. Within the hyperbolic geometry, the sum of the angles of a triangle is always less than 180 degrees. The elliptic and hyperbolic geometries were the two major paradigm shifts which occurred within 2,300 years. Those two radical shifts fundamentally changed the way geometers think about geometry. Similarly, the world's fastest computing across the world's slowest processors is a radical shift that changed the way computer scientists think about their supercomputers. Parallel supercomputing is a fundamental shift in the way we compute, just as the theory of evolution changed the way biologists think. Supercomputing across up to 1 billion coupled processors fundamentally changed the way the most compute-intensive problems are solved, and changed it, just as the heliocentric worldview changed the geocentric worldview of astronomers who preceded Galileo Galilei. Parallel supercomputing changed large-scale computational physics the way the modern physics of Albert Einstein changed the classical physics of Isaac Newton. At its essence, the fastest supercomputer that I discovered at 8:15 in the morning of Tuesday, July 4, 1989, was about changing from the computer that solved one problem at a time to the supercomputer of today that solves up to 1 billion problems at once, or changing to the internet of tomorrow, which is still in the realm of science fiction, that could become the planetary supercomputer of the future. Parallel supercomputing was a fundamental change of tectonic proportions that changed the way we study computer science. In their old computer science, the computer solved one problem at a time. In my new computer science, the computer solves many problems at once. A man said to his pediatrician, "Do you know Philip Emeagwali?" I wrote an inventor report on Philip Emeagwali. My daughter also wrote an inventor report on Philip Emeagwali. His pediatrician smiled and said, I also wrote an inventor report on Philip Emeagwali. My son also wrote an inventor report on Philip Emeagwali. For the 12-year-old that is writing a school essay on inventors and their inventions, an essential question is this: what is Philip Emeagwali known for? I was the first person to discover that the slowest processors in the world could be harnessed and used to power the fastest computers in the world. That new knowledge is used to solve the most compute-intensive problems in the world. That invention is the reason the fastest computers in the world are powered by up to 10.65 million processors. I discovered how an ensemble of up to 1 binary billion processors can be married together by as many email wires and messages. A binary billion is 2 raised to power 32, or 4,294,967,296. And then use those processors to solve the most compute-intensive problems. I discovered how to fuse processors and do so to, in reality, form one coherent unit that's a never-before-seen machinery. That's the world's fastest computer that made the news headlines in 1989. That new supercomputer, which is also a new internet that I invented on July 4, 1989, is radically different from the constituent processors from which it originated. The world's fastest computer, as it's known today, originated from the slowest processors. My historic run was the first world's fastest computing across the world's slowest processors. My breakthrough occurred at 8:15 in the morning on July 4, 1989. I was its first eyewitness. For that reason, it was a visceral experience. My visceral cries drew a little crowd. People down the hall ran towards me as they heard my visceral cries for my discovery of the world's fastest computing. I cried because it was the first supercomputing that will change the lives of our descendants, and do so by permanently changing the way our descendants will look at their world's fastest computers. Each person that heard my visceral cries was puzzled by my emotional reaction to what seemed incomprehensible, namely the world's fastest computing that I executed in a new way that will forever change the way we look at the computer. My supercomputer run performed 3.1 billion calculations per second. That was a world record for July 4, 1989, that opened the door to the modern supercomputer. I used those 65,536 processors to solve a system of 24 million equations of algebra. In addition to my computing speed, the number of processors and equations were both world records. My 3 world records in speed, processor, and equations were validated by the computing and petroleum industries. The supercomputing industry now incorporates parallel processing, and the petroleum industry now purchases 1 in 10 supercomputers. Oh yes, harnessing a billion processors gives the right answer too. When I began supercomputing back on June 20, 1974 in Corvallis, Oregon, USA, the world's fastest computing across the world's slowest processors was science fiction. 15 years later, on July 4, 1989, in Los Alamos, New Mexico, USA, I discovered how to turn that science fiction to reality. For that contribution, I became the first and only person to win alone the highest award in supercomputing. The world's fastest computing, as it's executed today, was the pseudoscience of the 1980s and earlier. The turning point was my scientific breakthrough that occurred on July 4, 1989, and elevated that pseudoscience to science. How do I want to be remembered? I want to be remembered as the supercomputer inventor that connected those dots or vertices or processors, so to speak. I want to be remembered as the supercomputer discoverer that told the coherent story and discovered those internets as, in reality, coherent computers that are the fastest. The genius is the ordinary person that found the extraordinary in the ordinary. My invention of fastest computing is summed as follows. The slowest processors can cooperatively compute together to yield the fastest computation ever recorded and to solve the most compute-intensive problem ever solved. My discovery is used to combine computers into supercomputers and can be used to create a supercomputer that's an internet. Thank you very much. I'm Philip Emeagwali. Thank you.
Insightful and brilliant lecture.